we're taking the derivative with respect to t on both sides. So the left side, okay, all d dt is doing is saying, hey, what's the derivative of this with respect to t? Okay, so the left side is the derivative of area with respect to time, right? dA, how is area changing? Over dt means as time changes. Like verbally, what I'm saying, I'm giving you like the English, and then I'm writing the, not acronym, the shortened version, you know? So dA dt just means how is area changing with respect to time. So as time changes, how does that affect area? That's all this is saying. The right side. Okay. So this is kind of weird.
Do we do it for each and every room?
Yes. So we have u, and this is v. I have b times h. Those are separate variables. And we have a product. So I have to use u and v, product rule. So I have 1/2 b times dh dt plus the derivative of, let's see, 1/2 times the derivative of b. So 1/2 db dt times h.
You did it.
You did it? It's because I loosened it for you. Okay, I'm just gonna screencast. That's not all we did. We did like 2 problems.
I'm sorry.
And
Make
open.
her feel better.
And open putty. Okay. So, what?
Is it going to be That's our school.
Is it clean? Nice. It is now.
Now, we want to find. Yeah. So keep in mind, we had to use product rule because we had 2 things being multiplied together. Because we don't know what the derivative of b is with respect to time. We don't know what the derivative of h is with respect to time. So theoretically, b is a function with respect to time that describes how the base is changing as time changes. H here is a function that's telling you how height is changing as time changes. That's why I had to use product rule. I know someone's literally going to ask me, why do we use product rule here? I just explained. Huh?
How do we know that's the 1/2?
It doesn't. We could just do 1/2 out front because the derivative of a constant is constant. It is, right? Sorry, not constant, but if you take like 1/2 b and try to take a, like 1/2 x derivative is, 1/2, right? So I could just put the 1/2 in front because it's in both terms. Okay, let's try the next one.
Can you go up for like 2 little seconds?
What? I just did. I literally just did.
That's it. Thank you.
Okay, so let's ddt. Come on. Take the derivative with respect to time. Should I make screencasts for lessons so if we don't finish, I'll say watch it for homework?
No.
All right. If I do that, that means I won't be messing with putty anymore either. So let's not do that. Let's focus. So v equals 4 pi r squared, right? I'm going to write it as, let's see, volume is 4 pi r squared. Because remember, it said h is 4, so I just plugged it in for h. So if I want the derivative with respect to time, dv dt is going to be, okay, I have to take the derivative with respect to time of 4 pi r squared. So implicit differentiation, this is going to be the same thing as 4 pi times 2r times dr dt. Now before, right, the last example, we had b, and then we take the derivative with respect to time, it was db dt. But here, we don't just have r, we have r squared. So we had to take the derivative of r, okay, well that's just going to be 2 times r, and then the derivative of r with respect to time. So this is where implicit differentiation comes into play. So dv dt is going to be 8 pi r times dr dt. So what this is telling you is, if I have an equation for how radius is changing with respect to time, I could pick at any moment and figure out what the radius would be, how it's changing, etc., etc. Or if I'm saying, okay, when the radius is 2, the volume is 8, what is the rate of change? Like you could solve for it The rate of change of radius with respect to time is dr dt, yeah?
I don't understand how you use that to really find it. Like, I get that it, like, in your head, it means something, but like on paper, can you use 8 pi r dr over dt to...
Yeah,
Can you
I
track
could say at time equals 5, right? At 5 seconds, my radius is 10, my volume's 100. What is my rate of change at that moment? Well, dr dt is my rate of change at that moment. I just told you the radius was 10. I told you what the volume was, right?
Also, the derivative of the radius of the derivative of time.
So dr dt is telling you how the radius is changing as time changes. That's literally your rate of change.
Yeah.
Yeah. So we're gonna like have problems where we're using it, but trying to get you guys to like be able to work in other variables. That's the goal of here and reviewing implicit. So just throwing you into these problems that are like difficult. I'm not gonna lie, they're not easy. They're difficult. Tall.
Why in example B did you use a probable with variables?
Because h was 4 and I only had one variable, which is r, versus in B I had b and h. B is base, h is height.
So like why did
If I didn't, then I'd have to use product rule here. If I didn't tell you h was 4.
you
So
do
this-
4
what?
pi r squared, which is over you do like 4 pi or u r squared is 2.
I'm sorry, repeat one more time.
I'm saying like how do you know not to use it? Because if I look at that I can say like oh like 4 pi is my u and r squared is u.
4 pi is a constant. Derivative of a constant is 0. 4 pi is a number.
Is it a constant because there's no variable?
4 pi is a constant because there's no variable. Pi is a number. 4 pi is like 12 point something, 13 point something.
Oh, I see.
Because it's a number, yeah. So this is just a constant, and then I have a single variable. Okay, so remember how I asked you what dx of y squared was? Yeah, we had to take the derivative of y and then multiply it by dy dx. That's exactly what we did with our r just now. Okay, I don't care if you're playing with putty, but you gotta make sure you pay attention, okay? Okay, cool. Because it's test is coming up, and I would love to have a 10% average higher. 10% average that's higher.
So what was the average?
Like a 72%. Yeah.
I have a question.
That.
How are we finding DDT if there's no T in any of these?
Right, that's why we keep having these like random things at the end, right? We had dr dt, we have db dt, dh dt, because none of these are defined with respect to t. Theoretically, there should be an equation that tells us how radius changes with time. Maybe radius changes with time that just,
T time?
yeah, t stands for time.
Maybe, okay. I think I should, okay.
All right, let's try this next one. D. Y is equal to tan of theta. So I want to take the derivative on both sides and with respect to t. Because most times things are changing, it's always with respect to time. Oh, how fast are you going? Okay, so that's how much distance. That's how distance is changing with respect to time. How is the score changing? Oh yeah, you're going up 2 points per minute, right? It's always with respect to time. Time is always our independent variable. It's physics, with chemistry, with bio. We're always looking how things are changing with respect to time. Because that's the thing that always changes. Always goes forward. Okay, taking the derivative with respect to time, right? Because that's t. Keep in mind, right, d dx of tan of x. So literally, just a plain derivative, right? Taking the derivative with respect to x, tan x is in terms of x. That's just going to be secant squared x. And then times 1 because the derivative of x is just 1. So secretly we've been doing chain rule the whole time. That's just secant squared x. Okay, so when I take the derivative with respect to both sides, dy dt is equal to, what's the derivative of tangent? Secant squared theta. Okay, well that's literally what I just wrote. Derivative of tangent is secant squared. So if I say what's the derivative of tangent, secant squared, and then times by however theta is changing with respect to time. So times d theta dt. Because I have this equation, tan of theta. Okay, well how is that changing with respect to time? Well, I don't know the relation between like theta and time, right? Is is theta equal to time? So, every second we're just increasing to the degree by 1, or is it like exponentially increasing, or, you know what I mean? There has to be like some relation telling how my angle's changing with respect to time. So this is it. Okay.
But we can't, how are we defining time? We don't know if it's seconds,
This
minutes, we don't know.
Right, that's why we just have dt. Because right now I'm trying to make this as like foolproof as possible. I haven't given you a problem where I define that yet.
So like,
But what I am going to be using is like derivatives with not just like in terms of x, in terms of t, in terms of v, like trying to get you used to other.
So essentially, if you gave us a time, we would find that first and then plug in for time.
No, not at all.
Okay.
But it's fine, okay? Because like I'm really trying to like break it down for you. I don't know if this is like going too slow because the questions you're asking like will be answered when we get to the real problems.
Okay, sure.
Yeah, like if you look at example 4, just like turn your page, look at example 4. Example 4.
Oh.
Right. Issue is if I started with that problem today, no bueno. That's why we're going through the easier stuff first to like try to prepare you. Think about if you try to go play basketball right now. Like, no, you need a ponytail holder, you need water, like these things you need, little components. Come on, just play with it, okay? You need these little components, and then we're going to put them all together. That's what we're doing right now. I'm giving you little components, and then we're going to put them all together for like a hard problem.
Okay.
But I want to make sure all the little steps you can do individually, so that way theoretically you can do it when we go all together. Okay.
Sure.
Example 2. The radius, r, height, h, and volume on a right of a right and blah, blah, blah. Okay. Of a right circular cone are related by volume equals 1/3 pi r squared times h. How is dv dt related to dh dt if r is constant? If r is constant. You ready?
Yes.
Okay. So dv dt, what I'm going to be doing is taking a derivative of this equation with respect to time. Okay. So dv dt. And I want to take the derivative of 1/3 pi r squared times h. Wait, we said r is constant, right? So here we'll treat it as a number, right? Here r squared, we're holding the radius constant, and the only thing we're changing is the height of the cone. Do you know what I'm talking about? Like this. I have a right, oh my god.
Yeah, when you have a cone with the paper.
Like I have a cone, right? What I'm doing is I'm holding this radius constant. What I'm doing is I'm going to be changing the height of the cone. Right, so I first start with a squat little cone, and the radius stays the same, but it just gets like a higher and higher cone. So if I'm keeping the radius the same. This could be my first cone. Maybe this is my second. I just get taller and taller and taller. Right, I want to see how volume is changing as height changes. And I'm keeping the radius the same. That's what this problem is saying. Okay. Treating r as constant. So if it's just a constant, it's just a plain number. It means this whole piece right here is just a number. Whatever my radius is. Because I could go through and I could see like, okay, how is height changing if my radius is 1 inch? How is my height changing if I keep my radius at 2 inches? Right? So I could pick a number and then see how it changes. Let's make the radius a little bigger. See how the height changes with volume. Okay. So if I'm treating it as a constant, dv dt is just going to be 1/3 pi r squared times dh dt. Because r is being constant. Oops, make this an h. Okay, we're going to do the same problem, except this time we're keeping the height the exact same, all right? We don't want a 10-foot tall cone. That's dumb, right? Like we have people who are 6 foot tall. I want them to be able to walk through the door without having their cone fall off. Okay, keeping the height of the cone the same. What this means is I could have a cone that looks like that. I could have a cone that looks like this. I could have a cone that goes real wide. So this time we're keeping height constant. We're increasing the radius. Does that make sense what I'm doing with my cones here? Okay, so if h is constant, I want to take the volume, how is volume changing with respect to time? How does volume change as time goes on as the radius increases? Cool. So let's see. So I'm going to take d dt of the right side. So 1/3 pi r squared times h. H is a constant this time. Okay. So dv dt. I'm going to write out all my letters. 1/3 pi times h because it's constant. And then I got to take the derivative of r squared. Derivative of r squared is 2r times whatever dr dt is, right? Depends how fast my radius is changing with time, right? Is my radius changing like 1 inch per minute, 1 inch per year? Like, how is it spreading? How is it getting bigger? How does that impact? So how does the rate of change of how much bigger my radius is getting, how is that related to the change in volume, you know? Okay. So to simplify this a little bit, dv dt is just going to be 2/3 pi hr times dr dt. Ooh, and lastly, what if I'm not keeping height constant or the radius constant? What if like things are changing, like both height is changing and radius are changing at the same time, right? They both have a function that's defining how they're changing. How will my radius change? I'm sorry, how will my volume change with respect to time? That's the last question. So now neither one of these are constant. So I have to use product rule. We have to use product rule because neither one of these are constant. So what?
Why are you writing like that and not?
I mean, I was showing taking d dt of both sides. So dv dt is going to be equal to, let's see, pi over 3 times d dt of r squared h. Because it's just, I pulled out the constant. Okay, so now I have product rule. I have two different functions, right? I have a whole function secretly where r is in terms of t. Maybe like r of t is equal to like 4t. What this means is the radius, every second, the radius is getting bigger by 4, right? Maybe. This is like secretly, this is behind the scenes. We don't know this. We don't know the actual equation. In actual problems, like I'll tell you, or this is what you'll be solving for. And maybe height is changing with like negative 1/3 t squared. So as time goes on, it gets smaller, but it's like exponentially shrinking or something, you know? These aren't actually like given to you, but I'm trying to explain why we have to use product rule, because radius is in terms of time, but like you don't know the actual equation. That's why we have to use implicit differentiation. So we don't actually know this, so you have to actually ignore those numbers. Sorry. Yeah, Hannah?
If we're finding the derivative of 1/3 pi r squared h, how are we able to take out the constant? Because
it will be in both, because if I have like,
because you didn't take the derivative of pi over 3.
I didn't, but it's a constant, so I can pull it up front.
So
Because
the derivative of
so if I take, don't write this, derivative of 1/2 x is just 1/2, right?
yeah.
It's the same thing as taking 1/2 times derivative of x, so it's just 1/2 times 1. So I just pulled it out before I took the derivative.
Okay.
Yep. Okay, so use product rule. So dv dt is equal to pi over 3 times, okay, u times v squared, I'm sorry, u times v prime, so r squared dh dt plus 2r dr dt over times h. Because here u is r squared, so u prime is going to be 2r, v is h, v prime is h is 1. But don't forget, if we're taking it with respect to t, you have to tack on dh dt and tack on dr dt. So that is the answer for this guy. Okay. Bringing you into this slowly at first, right? So first we practiced implicit differentiation. Then we said, okay, we have this whole equation. What's happening if this is constant? What about if this one's constant? What if they're not like both changing? What if they're both changing? How is that change? How is that working? And now example 3, like every example is just getting you deeper and deeper into what we're really trying to do with this section.
Why did you write the PhD not the R squared?
Because technically it's r squared times 1 times the derivative of h with respect to time. This is 2r times the derivative of r with respect to t.
The derivative of H is just
Yeah, fine. 1 times dh dt.
yeah, I don't
2r times dr dt. Huh?
I don't care why you still want.
Because I'm taking the derivative with respect to time. H is a function.
Oh, and it's not time, so it's like when you find
H is not
the
time,
y.
but h is a function with time in it. Yeah. Okay, let's
So it's like finding what we did a while ago when you find the derivative
implicit
of y.
differentiation.
Yeah.
It's exactly implicit differentiation. Yep. It is 3.7. 3.7 implicit. What's
So
wrong?
just tack on the thing that's not the constant.
Yeah, if we're taking with respect to time, just tack on the dh dt. Like when we're doing implicit, we had to tack on a dy dx. So, okay. So example 3, the base B of a right triangle is increasing at a rate of 3 centimeters per second. So it's telling us the rate of change of the base with respect to time. So guess what this is? dB dt. It's telling us how base is changing with respect to time. While the height is decreasing at a rate of 2 centimeters per second. Okay, height decreasing 2 centimeters per second. That's telling us the rate of change, right? That's telling us how height is changing with respect to time, aka dh dt. dh, how is height changing over dt as time changes. So decreasing is negative 2 centimeters per second. When b is 4 and height is 3, find the rates of change of area, length of hypotenuse, perimeter, angle theta, etc., etc. We have like 1-2 minutes, so we have to finish this tomorrow. But what I want to make sure you do, like for instance tonight, you're not going to be able to do any of the 4.6 problems, but what you could do is some of the review. There's literally 1 page of quick review, and there's 1 page that's reviewing chapter 4. So you could knock out assignment 7 today. Get it done. It will help you.